Morning, everybody. So last time we started talking about NMR, which stands for nuclear magnetic resonance, and we learned a little bit about what that technique is. And we were talking about proton NMR, which allows us to look at hydrogens, right? What kind of information can we get from the proton NMR? Well, ultimately we can get structure, but what kind of information are we getting that leads to structure? What can we get? We can get chemical shift, which tells us what? Right, tells us it's an electronic environment. Very good. So things that are attached to electronegative elements or close to them will be shifted further upfield or downfield? Downfield. Very good. Right. Things that are not attached to things that are very electronegative will appear further upfield. What else can we get? Peaks. What kind of peaks? That's chemical shift. What else can we get? Yep. What else can we get? What other pieces of information do we get just by looking at that NMR? You're going to have no more than just chemical shift. Okay, we can get the different types of signals, so we can get the number of unique environments. Very good. What else can we get? We can see the number of neighbors that a particular set of protons has, right? How do we get that information? By the splittings, right? So we look at the splitting. So if a signal is split into a triplet, it means it has how many neighbors? Two. It's n plus 1, right? If it appears as a doublet, a quartet, okay, and so on and so forth, right? What else can we get? So we got kind of the environment, the splittings. What else can we get? The relative number, using what piece of information that we can get? The integration, or the peak integral, right? The area under that curve. And so let's look at a couple of other examples here. So here we have, how would we name this alkyl iodide? Pardon? What iodopentane? 2-iodopentane, or not pentane, propane, excuse me. I don't know where we're coming up with pentane. Propane, because there's 3, right? Will everybody agree that we're going to see 2 unique signals? Right? Both A's are identical because of what? There's plane of symmetry, and B is clearly different, right? It's in the plane. So if we look at it like this, you can see the 2 methyl groups are identical. So think in your mind, what should A look like? What should the peak look like? Should it be upfield or should it be downfield from the other peak? A should be downfield of B? Which one's the closest to the iodide? B is the closest to the iodide, so it should be further downfield, and A should be further upfield. What should the splitting be for A? How many neighbors does A have? So it should be a doublet. And B has how many neighbors? So it should be it should be 7 peaks, right? A septet, right? 7 is fine, okay? And you'll get a structure that kind of looks like this. You can see the doublet at just under 2, and you can see the multiplet at about 4.3. And if you look really carefully, right, you can see 1, 2, 3, 4, 5, 6, 7 peaks. If you look at dichloroethane, 1,1-dichloroethane, notice how far this peak is coming downfield now for B. It's a single proton. It's got 3 neighbors. It appears as a quartet. But it appears as a quartet around 5.9. What's the hybridization of that carbon atom? Is it sp2? It's sp3, but it's appearing in the region that you might expect to see in sp2. That 5 line that I told you to draw is just a rough guide. Why does that B appear so far downfield? Because it's got twice as many electronegative atoms. That's exactly right. So it gets pulled down even further, right? A, right, has a single proton that's its neighbor, these 3 protons, and so you see the doublet here just after 2, about 2.05 or something like that. If you look at 1,3-dichloropropane, again, we're going to have 2 unique signals, A and B, right? And you can see the splitting. A is going to be further upfield or further downfield? Further upfield, right? It's the one here at about 2 point, what is that, about 2.2, right? How many neighbors does it have? So it should appear as 5 peaks. And in fact, that's what we see. 1, 2, 3, 4, 5, right? Protons for B have how many neighbors? And it should appear as a triplet. In fact, it does. And if we got our rulers out and started measuring these little integrals, you would see that the integrations were spot on for the relative number of protons. Okay? Lots of information. We're getting chemical shift. It tells us what kind of environments the protons are in. We're getting peak splittings, which tell us something about the neighbors. We're getting integrations, which tell us something about the relative number. And we can sit there and take these pieces of information and put them together just like a jigsaw puzzle and come up with a structure. When you're doing this, you need to write out what you think the structure is. So if I gave you a spectrum and a molecular formula, say for this, you should be able to predict that it's this structure. But you actually have to put together the pieces of the puzzle and see if they make sense to the data. If they don't make sense to the data, they can't be correct, and then you have to rearrange things, right? So you may have come up with other ways in which you can connect the atoms, for example. But it all has to match at the end, okay? So here we have nitropropane, 1-nitropropane, and you can see TMS. What's TMS again? It's our standard that defines what? It defines 0 on this chemical shift scale for us, right? So we have TMS, we have protons A, B, and C. Does it make sense that C is so far downfield? Why? Yeah, and that nitrogen has what kind of charge on it? For a nitro group? It's a positively charged nitrogen. It is a nitrogen that has 4 bonds to it, okay? So the nitrogen itself actually has a formal positive charge. One of these oxygens actually has a formal negative charge, and so it's overall neutral. But that's going to pull these protons way downfield, right? And so you're going to see them around 4.3, 4.4, right? 3 neighbors, so it's going to be, or excuse me, 2 neighbors, so it's going to be a triplet. How many neighbors do we have for B? We got 5 total neighbors, so it should be 1, 2, 3, 4, 5, 6, and in fact it is. This is all well behaved. And A has how many neighbors? And so it should be A, and in fact it is, right? And so you can see on the scale there the different electronic environments. No integrals are shown on this one, but if we had it integrated, you would see that information as well. So, how do peak splittings come about? What is so magical about these neighboring protons that give rise to different peaks? It turns out I'm going to have to teach you a little bit of statistical mechanics, which is a higher level physics class, but I'm going to give you just the bare bones of it today, okay? And it's all about probability. Nature is really well behaved when it comes to probability, okay? So if we imagine having a proton that is just by itself, you can't really have that, but imagine that you have a proton all by itself that's in the NMR. Has nothing that interacts. You're going to see a singlet for that because there are no neighbors. And the only thing that it feels or it is experiencing is the magnetic field of the NMR spectrometer. All it is feeling is B0. Remember, B0 is what we use to abbreviate for the NMR's magnetic field. However, now imagine that I've got that proton and I give it a neighboring proton that is not equivalent. So it'll split it. What does that proton now feel? It feels the magnetic field of the NMR spectrometer just like it did before, but now it's got a neighboring magnet. Remember, a proton is a spinning thing, right? And spinning charges are electromagnets. And that neighboring proton can either spin in what direction? It can either spin up or it can spin down. Can it spin anywhere else? It's quantized, right? It can either be up or down. So what's happening? Well, the proton that we started with is feeling B0 plus the magnetic field from the neighboring proton, but that has two states, either up or down, and these are different magnetic fields. And so you end up with a doublet. What's the probability of spinning up or spinning down? In the 50-50, right? And so that's why a proton that has a single non-equivalent neighboring proton will couple, as we call it, because that proton is feeling the magnetic field of the NMR spectrometer plus the little magnets that are around it called protons. And that gives rise to different chemical shifts, okay? And so you actually have a doublet in that particular case. Pretty simple. Things get a little more difficult when you start to talk about a triplet. Same concept, but now you've got more possibilities, right? If something is a triplet, how many neighbors does it have? It's got two neighbors, right? Well, that proton's going to feel B0, right? And it's got two neighbors, and we just call them A and B. So it could be B0 with A and B both in the same direction as B0. It could be B0 with A and B opposite to B0. But notice that we can have A and B in opposite directions, right? And so that's how you end up with this ratio of 1 to 2 to 1 in a triplet. A pure triplet will actually be 1 to 2 to 1 in terms of their peak heights. And it's because there are 4 different ways in which these neighboring protons can be oriented with respect to B0. And that's why you see a triplet. Okay? Does this make sense? The magnetic field that that proton is experiencing isn't just B0. It's B0 plus the little magnets that are around it. And those little magnets can either be aligned with or against the magnetic field of the NMR spectrometer, right? And so when you look at the possibilities, that's how you end up with these peaks being split as they are, okay? Let's look at a little bit of a concepts test here. This comes from the ACS exam guide, so these are types of questions you might expect to see on the ACS exam. This comes from that style guide on page 143, so if you have a copy of it, you can follow along. Signals from how many sets of protons would be observed in the proton NMR spectrum for this compound? In other words, how many signals are we going to see? How many signals do you think we're going to see, Chase? Okay. Want to take a guess, Anna? No? It's Monday morning? 5? Actually, we're going to end up with 6. Where are they? If I look at this molecule, there's a mirror plane that runs right through here. There's no protons on this carbon or this carbon. It's 1, 2, 3, 4, 5, and 6. Because there's a mirror plane that runs right through the heart of it. Which structure is consistent with this NMR spectrum? What do we do? What do we start with? What's the first thing we do? Draw a line at 5. Does that help us here? Doesn't help us here, but we're going to draw a line at 5, right? What's the next thing we're going to do? We're going to count the number of unique proton environments. How many do I have? 3. Remember, we don't count 0, right? So I've got this one, and this one. So that's a quartet, that's a singlet, and that's a triplet. So I've got 3 unique environments. Is there anything I can eliminate based on that? Well, I don't know. There's a mirror plane here, right? So 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. There's 4 unique environments there, so that doesn't work, right? And there's 3 there. So I can eliminate 1. Haven't gotten to 50-50 odds yet. Now what do we do? Well, we've counted the number of signals already. What do you mean by counting the number of peaks? The splittings? Yeah. Okay, so we got a singlet, a triplet, and a quartet. That would be a singlet. That would be a what? Quartet, and that would be a triplet. That fits. That would be a triplet, quartet, singlet. Wait, those seem the same, don't they? Can't really tell there. How about here? So just by counting the splittings, we can't really tell. So now what am I going to use? I've got something else here for a reason. What do we have to rely on now? The chemical shift. And what do you notice? The quartet is really far downfield, meaning that it must be attached to what? Something electronegative, right? In this case, oxygen. So which one would that fit? Wouldn't fit all of them. Actually B. Right? Because these 2 hydrogens are on a carbon directly attached to an oxygen. That's going to be the furthest downfield. So that quartet is going to be the furthest downfield. That triplet will be upfield. And then this singlet will be further downfield than the triplet because it is next to these carbonyls, but not as far downfield as the quartet because they're not directly attached to the oxygens. Right? So we can use all of our techniques to try to figure out that structure. Okay? All right. Today we're going to get into a little bit of carbon NMR after we do a little bit of more practice on the proton NMR. We probably won't get to mass spectrometry today. We'll cover that on Wednesday a little bit. And so let's get started. So that doesn't show up very good. So when we're trying to determine the structure by proton NMR, there's 4 things that we need to do, right? We need to determine the number of signals. We've already gone over that. We need to determine the chemical shift. We need to determine the integration. And then we need to determine splitting patterns. If we look at this simple little molecule, alpha-methylstyrene, what we see are how many environments? We see one here, 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 and here. So that's how many? We see 6 unique environments. This simple little molecule actually has a fairly complicated NMR spectrum. Okay? Where do we draw the line? We draw a line at 5. And what we notice is that we have one signal over here that's a singlet, right? Or at least it appears as a singlet, that's in what region? It's SP3 region. And which one is that? Which carbon atom, or which hydrogens on which carbon atom is that? It's this methyl group, right? Okay. What are these two protons? The ones at 5 and about 5.5. They are sp2. Which ones are they? Are they on the benzene ring or are they on the alkene? They are on the alkene. They are these two hydrogens. One of them here, one of them there, right? They are different. Why are they different? They're both on the same carbon atom. Why are they different? Why do they give different chemical shifts? Why are they not equivalent? Okay, very good. So we have one hydrogen that is cis to the methyl group but trans to the aromatic ring, and we have one that is cis to the aromatic ring but trans to the methyl. They are not equivalent. They are different. So they will appear in different environments. These three peaks that you see here are on the aromatic ring. Wait a second. Why should I only see 3 peaks when there are 5 protons on that aromatic ring? Pardon? Why? What symmetry element dictates that? There is a mirror plane. And as it is drawn, you can't see it. But if you rotate around this sigma bond, so if you imagine that my hand is the aromatic ring, and you imagine this being the alkene, it's not really like this. It's kind of like that. And so there's a mirror plane that runs this way. And so we have 1, 2, 3 unique environments. Which proton is this one? The furthest upfield or the furthest downfield? Say it again. Furthest downfield. All right? Furthest downfield. How many neighbors does this one proton have? 2. So it should appear as a, and in fact it does. It appears as a triplet. So we can get a lot of information about a simple molecule pretty easily from this type of analysis. Okay? So let's look at some more from our ACS study guide. Which of the following structures is consistent with this NMR spectrum? Do we count 0? On number 4? These? So does that look like anything we've talked about? Or does that look like 2 signals that just happen to be really close? Probably 2 signals that are really close, right? If I looked at that, it kind of looks like a quartet and a triplet that are just really close to one another. What can we eliminate? We can eliminate A. Why can you eliminate A? Not enough proton environments? 1, 2, 3. Oh, there's 4. There's 4, right? But I still argue you can probably eliminate A. Why can we eliminate A? That's right. So if we have a hydrogen on a carbon with 2 chlorines, how far downfield would we expect that to be now? We'd expect it to be past 5. Is it past 5? Nothing there. Okay. What else? eliminated A. Somebody take a guess. C is the right answer, right? So if we look at this, we should have a triplet that is pretty far upfield. We should have a quartet, which is pretty far downfield. We should have a triplet, and we should have another triplet that is pretty close to where the other triplet is going to be, because chlorine and oxygen are about the same electronegativity. So they're going to be really close to one another in that environment. Which structure is consistent with this NMR spectrum? Count the peaks. Quartet will have 4 peaks.
Is it based on what's bonded to the hydrogen, or?
It's based on the neighbors.
Is it A?
No. There's 2 things that I'm looking at there that really help me out. We've drawn the line at 5. We've looked at all that stuff. We've counted the number of signals. But there are 2 pieces of information on that spectrum that I'm really honing in on. Number 1, I've got a singlet at about 10. When we talked about our chemical shifts, things that appear out about 10 are going to be things like carboxylic acids or aldehydes. Do I have either of those? Do I have anything with a functional group of an aldehyde or a carboxylic acid? Which ones? A and C, right? And I just discounted A, right? So that gives me an idea it's probably going to be C. But what else am I looking at that keys me into it being C? The nitrogen has something to do with it. Be a little more specific for me. What about it? What I notice is that there's symmetry in this molecule, right? Because this benzene ring is 1,4-disubstituted, there's a mirror plane that runs through here. So I'm going to have a doublet and a doublet. Anytime around 7 you see this pair of doublets like that, usually what that means is you've got a 1,4-disubstituted benzene ring in your molecule. So when I see a splitting pattern that looks like that around 7, I instantly think about a benzene ring with something at carbon number 1 and something at carbon number 4. And when I do that, that really limits it to B and C. B does not have an aldehyde, which I clearly see here. The answer has to be C. And so what you can see here is this CH2 has 3 neighbors, so it's going to be a quartet. The methyl group has 2 neighbors, so it's going to be a triplet, and you can see that everything else falls into place quite nicely there. How about this one? What are these numbers up here? 1H, 2H, 1H, 6H? Those are the integral values. Yeah. Relative number of protons. Can we have a single carbon atom with 6 protons on it? No. So what does that tell us? We have 2 equivalent carbon atoms, each with how many protons? 3. What group has 3 protons on a carbon? It is C. right? Those two methyl groups are equivalent, right? And they have how many neighbors? No, how many neighbors do these two have? They're equivalent. They have one, so it's going to be a doublet. And in fact, that's what we see here. We see a doublet. This proton is this proton, right? And it has how many neighbors? It's got 6. It's got 8, right? This proton has these 6 and then these 2. It's got 8. So how many peaks would that be? And let's see if it's right. 1, 2, 3, 4, 5, 6, 7, 8, and the little tiny one there, 9. Yep, it works. These two protons, you only see 7 what? Well, it's right there. It's hard to see. But you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So, well, this hydrogen has how many neighbors? It's got 3, 4, 5, 6, 7, 8. It's got 8 neighbors.
I see that. I can't see all 9 peaks on the graph.
It's hard to tell by how it's blown up. But there's a little peak there.
Yeah, I see that one.
2, 3, 4, 5, 6, 7, 8, and 9. Now wait a second. Hold it. This CH2 is appearing as a doublet, right? But how many neighbors does it really have? It's got this neighbor. What about the OH? It does count. It is a neighbor, is it not? It's on an adjacent atom. So why is it appearing as a doublet and not a triplet? Also, if we look at the OH, it has 2 neighbors. Shouldn't it appear as a triplet? But it's appearing as a singlet. What did you all learn in your book about hydrogen atoms that are on heteroatoms? Things like OH and NH. Nope. There is no N-1 rule. It was a guess. What did y'all learn? What you should have learned is that hydrogen atoms on things like oxygen and nitrogen frequently do not split their neighbors. And it has to do with the fact that they can hydrogen bond, and hydrogen bonding leads to exchange. It's kind of a complicated process, but when something hydrogen bonds, that hydrogen doesn't really belong to that molecule anymore. It can actually migrate throughout the sample, and it exchanges on different molecules. And so the NMR can't get the NMR time scale of observing a molecule is actually pretty slow, and it looks like that proton is all by itself, if you will. There are ways in which we can get it to not do that. We can lower the temperature, we can change the solvent, but quite frequently alcohols and amines will appear as singlets even though they have neighbors, and they will appear not to split their neighbors as well. That's not universal. Okay? You have to know what you're looking for. Okay? But things that are OH or NH quite frequently do not appear to split or be split by their neighbors. All right, we need to move into carbon NMR just a little bit. Carbon NMR actually is, compared to proton NMR, it's a piece of cake. It's real easy. Okay? It's the easiest of them. The problem with carbon NMR is carbon-12 is the most abundant isotope of carbon, right? 97, 98%, whatever the numbers turn out to be, right? A lot of carbon is carbon-12, but carbon-12 has an even mass number and an even atomic number, and it is not NMR active. You can't see it. That's unfortunate for us. However, naturally occurring carbon-13 is about 1% of all natural carbon. Carbon-13 has an even mass number, or excuse me, an even atomic number, but an odd mass number. And it does give rise to NMR spectra, okay? And so it will give us an NMR spectrum, and we can look at the carbons. The problem is that it's only about 1% abundant. So you can go and run a proton NMR, right now with me, we could go down to the NMR spectrometer, put a sample in, and in 3 or 4 minutes, if everything's running right, we can have a spectrum. Because proton is very abundant. It's almost 100%, right? However, carbon-13, there's not a lot of carbon-13 around in your sample. So it's going to take a lot longer to run a carbon-13 NMR spectrum. So you can typically get a decent spectrum in about 30 minutes if you have a lot of sample. But if you have a very dilute sample, let's say you're making something and you've only made a few milligrams of it, you may actually have to run your carbon-13 spectrum overnight for like 24 hours sometimes. And so you're eating up a lot of spectrometer time, okay, which isn't cheap. The cool thing about carbon-13 NMR spectroscopy is that you really don't have to worry about splitting too much, and I'll tell you why that is in just a moment. And so the number of resonance will give you an idea of how many unique carbon atoms the structure has. So you can sit there and count, hey, there's 6 unique carbons in that structure. Does that mean that there are only 6 carbon atoms in the structure? No, it just means that there are 6 unique carbon atoms in the structure. Okay? The splitting tells you how many hydrogens are attached to the carbon. So if you see a carbon atom split into a triplet, it means that there are 2 hydrogens attached to that carbon. However, chemists rarely run in carbon spectra this way. We typically run them in a mode that decouples the protons, so we never really see that information. Okay? It makes things a lot simpler, and I'll show you why that is in just a moment. Okay? The chemical shift tells us the hybridization of the carbon atom, whether it's sp, sp2, or sp3. And the chemical shift is also affected by the electronic environment of the carbon atom, just like for proton, nothing new. Okay? Signal intensities in carbon spectra are not related to the relative number of carbon atoms. For the purposes of this class, you will assume you cannot integrate carbon spectra. That is a semi-lie, because there are techniques in which you can integrate carbons, but it's a much more higher level, complicated thing. Okay? The carbon chemical shift is not 0 to 10. The chemical shift for carbon spectra is 0 to 200. It's a much larger chemical shift range. That is good because it allows signals to be separated such that you can see them easily. Okay? Remember when some of those protons that we were looking at, the signals were getting kind of close to one another? Carbon, they're usually far enough apart that you can readily see them. Okay? Where am I going to draw the line? $100. Just like we drew the line at 5, which was halfway for proton, we draw the line halfway here. Everything to the right is going to be things like carbon-carbon triple bonds or carbon-carbon single bonds. Everything to the left is going to be sp2 hybridized carbon. Okay? This is the rough ranges in which you will find different carbon atoms. Okay? So we're going to draw that line at 100. Okay? In your book, you have tables of carbon-13 shifts. Again, that will be very useful for you when you go into lab and actually solve some serious structures that you don't have multiple choice guesses for. Okay? But on my exam, you really aren't going to need to know in this level of detail the shifts. You're going to need to know 100. You're going to need to know roughly where things are in terms of alkanes, alkenes, and alkynes, and that's about it. You'll be able to figure everything else out with the data that you're given. Okay? So here's an example of a phthalate. This is a simple molecule. What you will see is how many resonances. We see 1, 2, 3, 4, 5, 6. Notice the peak at 0 is actually quite tiny, but it's there. TMS is usually there, okay, as the thing that defines 0 for us. So we see these 6 unique resonances. 1 is at about just under 170. What functional group is that? It's not an acid, but it's related. If it was an acid, there would be a hydrogen on this. It's an ester, right? How many carbons that are equivalent to for carbon 1? 2. There's a mirror plane, right? So this is carbon 1 and this is carbon 1, right? Notice the peak height. It's tiny, right? Notice for carbon 5, it also has 2 carbons, but it's much taller. I can't use the peak height or the integration to tell how many carbon atoms are there. It just doesn't work. What else can you tell me about this? Carbon 5 has how many hydrogens attached to it? 2. So shouldn't it be a triplet? It should be, but it's appearing as a singlet. It's a technique that we use called off-resonance decoupling. Don't worry about that. I'm not going to test you on it. But what it does is it converts all the carbons into singlets, which makes it really nice because all you got to do is go 1, 2, 3, 4, 5, 6. You don't have to worry about splitting, okay? And so we know that we have these unique carbons. Carbons 3 and 4, and then carbon 2. Carbon 2 is really tiny, okay, compared to carbons 3 and 4. Again, we can't use the intensity to determine all that, okay? So this is diethyl phthalate. It's actually used in materials chemistry as a plasticizer in a variety of plastics, and you can see the different carbon resonances there. That's what it would look like if we ran it in the proton-coupled mode. It gets really nasty here. Things start to overlap. Notice this is now a triplet, as it should be. This is now a quartet, as it should be. Now imagine getting things that are really close in chemical shift, and you've got all these splittings. You will start to have a forest overlapping with a forest. And it gets hard to see the trees then, doesn't it? Right? And so you got to keep that in mind. So we typically run these in proton decoupled mode. Okay? So on ACS exams, you will quite frequently see things like this above a carbon NMR spectrum. S, D, T, and Q. What do those stand for? What does S stand for? Singlet, D, T, Q. All right. So every peak that you see here is actually a singlet in the proton-coupled mode. Everything that they say is a D would be a doublet in the proton-coupled mode. But notice they're showing you in the proton-decoupled mode. So everything is a singlet. But this tells me how many hydrogens. So how many hydrogens are on this carbon? If it's a singlet, 0. 0 plus 1 is 1, right? So 0, how many on this one? 1, 1, 2, 3. So using that information, which one of these structures is correct? Can you buy a what? Is it D? It's A. I thought you were playing The Price is Right or something. Or what is that, Wheel of Fortune? Yeah. So if we look at this, right, we've got a mirror plane of symmetry that runs through here. We're not looking at protons, we're just looking at carbons. So the first thing that you always do is count the carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 unique carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Can't be that one, right? So you just go through and count to start with, right? And this one would have 1, 2, 3, 4, 5, 6, 7. You just count the unique carbon atoms. So look at any kind of symmetry and count the unique carbons. If we look at this one, this carbon atom and this carbon atom are going to be sp3 hybridized, so they're going to be on this side of 100. This one has how many hydrogens attached to it? So it's going to be a triplet, and it's a little further downfield than this one, right? Because this carbon atom is not attached to the aromatic ring, okay? So it's attached to an oxygen just like this one is, but this one's also attached to an aromatic ring, which pulls it down just a little bit. And so there you have a quartet, you have a triplet, you have a doublet, you have a doublet, and then you have your 2 singlets because they have no carbon atoms on them, okay? If you ever see a little tiny triplet around 77, scratch that out as well. That is the solvent that we typically use to do the NMR spectrum. It's called deuterated chloroform, CDCl3. And it appears as a triplet because of the deuterium atom. Okay? But it's carbon, so you're going to see it in the carbon spectrum. All right, I'm going to hand back some stuff while you all think about this one. On Canvas, your grade for this inverted lecture will be +1 over what I have recorded here if you turned in that note card with that bonus question. Okay, so it won't match up. I promised everybody a bonus point. Jackson. Laurel. Holly. And by the way, I'm much more pleased with the arguments that were made here. Getting the hang of it. I like it. Anna, Savannah, Bailey, Shelby, Kaylin, Taylor Sims, Ashley, Nick, John, Mackenzie, there you are, Michael, Chase, Taylor, Gore, there you are. Megan, Ahmed, Catherine, is she not with us today? Key, Kara, I will say the one thing that probably cost people the most points on this one was your stereochemistry. So not taking into account the stereochemist. Logan, where's Logan? There you are. Jack. Garrett. All right, we'll finish up with this on Wednesday. Please finish reading up on NMR and on the mass spec part of the chapter. Have a great one.